Hey, what's up, Largo High School, and welcome to this edition of Wood's World. So today we're going to be looking at covalent bonding and adding in some intermolecular forces, looking at how those interactions react, how their three-dimensional shape affects things, and polarity. So let's get to it. I know that I have a hydrogen molecule, and hydrogen's group 1A, so therefore it has one electron. We know nitrogen. So if I'm looking at the periodic table, hydrogen is group 1A, so that's in that first group. Nitrogen is in the fifth group, therefore that has 5 valence electrons. And I know oxygen is in 6A or group 6, and therefore has 6 valence electrons. If I add all those up, that tells me that I have 12 electrons available. And how many do I need? Well, I know for hydrogen, we need 2 electrons. For both nitrogen and oxygen, we need 8. So there's 16, that makes 18. So there's 18 electrons. So therefore, I'm looking at the difference there. The difference there is 6. So therefore, that means somehow I'm possibly, so this is just it doesn't always work, but it's pretty close, that I'm going to end up needing 3 bonds, because 6 divided by 2, since there's 2 electrons for each one bond. So I know, and then once again, we want the one that is the fewest, but the closest to 4 valence electrons to be the center. So nitrogen here is going to be the center, and it has its 5. And I know that oxygen here is going to have its 6, and therefore hydrogen is going to have its 1. And so we have a bond between the hydrogen and nitrogen. We have a bond, and there's my 3 bonds. So technically it really looks like we know this lone pair takes up more space. So therefore it's going to push these down. So technically the oxygen is going to look like that. And we know the hydrogen is going to look like that, because this lone pair is going to take up more space. It has more electrons around it that aren't necessarily floating between the bonds. So therefore it's going to squash these down, causing this to be a bent shape. Right? So remember, bent, so this has, what is it, bent? So it has 1, 2, 3 areas of electron density, but 1 lone pair. So this is 3 steric areas, or 3 areas of electron density, and 1 lone pair. And I know that bent takes approximately 100, and so bent is somewhere somewhere around 114.5 approximately. These are all, and the angles, whenever they do these angles, the only reason that we know that these angles are like that is this is actually something that they measure in the lab. So these are actually like lab verified angles that they can, like, essentially almost like shoot a laser through these molecules and determine what the angle is going to end up being for that particular molecule between the bonds, that they can visually kind of measure that out. So bent somewhere around 114.5, somewhere in that neighborhood, less than 120. If this lone pair wasn't there, it would be 120, right? Because we have the 3 areas, but the lone pair causes it to be a little bit less than 120 degrees, or our trigonal planar. So bent has to be a little bit less, but more than our. Now this is the part that a lot of you guys were getting confused at, and polarity. All right, so this is so the periodic table with its electron negativity, or so electronegativity values. Notice fluorine is the highest, chlorine, right, a little bit lower, oxygen. So we can notice this increasing trend. So we have that general increasing trend going directly up. Right, so it's getting, so as these get smaller, the electronegativities get bigger, and therefore we can measure these values. So what we really look at is the difference in their electronegativities for an individual bond. So let's look back at the ones that we're looking at. So here, notice that between the nitrogen and this double bonded oxygen. So let's look at their values between just the nitrogen and oxygen and see what their differences are. So notice nitrogen has a value of 3, oxygen has a value of 3.5. So therefore a difference of 0.5 and slanted towards the oxygen. So the electrons want to be hanging out more towards the oxygen because it is slightly more electronegative, and therefore a little bit of a difference between 0.5. So here we know nitrogen had an electronegativity value of 3. This had an electronegativity value of 3.5, which means that this would become a partial positive and this would become a partial negative because the electrons are going to hang out more towards that or give me a dipole moment in that direction. So I'm going to get this arrow going towards the oxygen that way. Now let's look at the other side. So the other one we were looking at, hydrogen as compared to nitrogen. So I see a difference there of 0.9 or in favor of the nitrogen as far as the electrons. So the electrons are going to want to shift towards the nitrogen and not the hydrogen. So therefore the electrons in that bond are going to want to shift up that way. A difference of between 3 and 2.1. If I take one going up like that and one going down like that, and I add them together, what do I get? So I take the two together from tail to head, and their resultant is going to be directly that way. Right? So I got one going up, one coming down, which means that towards the hydrogen side is going to be partially positive, and towards the oxygen side is going to be partially negative, and therefore causing this difference in each of these bonds to be polar. So here, if their electronegativity values or differences are less than 0.4, then we would consider this nonpolar or purely covalent. If their electronegativity value differences are between 0.4 and 1.8, we would consider it polar covalent. Or if it's like halfway in between, so if it's like 0.4 to like, so for instance, if it's 0.4 to 0.8, we would consider this to be slightly polar. And if it's more than 0.8, it would be very polar. And then if it's greater than 1.8, those become ionic and therefore not covalent. They're not going to share their electrons at all. They're just one's going to steal them away from the other and give us that ionic bond and not the covalent bonds. And so that kind of gives us a little bit of idea on how to base these out for our electronegativity differences. So now this hybridization thing, so hybridization is based on its shape and how many different things are involved in the bonding. So here, notice we have 3 areas of electron density. So therefore, as far as my bonds, we have to have one of them is going to be using an s orbital in order to create one bond, or a sigma, what we call a sigma bond. So that's our sigma bond. Then we have 2 others that are going to have to use p orbitals in order to share their electrons. So 1s and 2p gives me all 3 areas. So therefore the hybridization is using 1s orbital and 2p orbitals in order to share these electrons. And so we call this sp2 hybridization. For the intermolecular forces, there are a couple of different ones. So the ones that we talked about London dispersion forces, So let's first talk about what options we have. All right, so the options we have, one of them we have ionic. Well, we're not talking about ionic. So ionic would be between some kind of metal and non-metal, like for instance a sodium that has a +1 and a chlorine that has a -1 charge. So here we have this electrostatic reaction that holds them together. Dipole-dipole would be if you have two polar molecules that are mixed together. So for instance, the one that we just had, HNO. So because the HNO is going to be so this is going to be mixed. So we know this was that structure, HN, right, with the double bonded O, with our slightly positive on the N, slightly negative on the O, due to the dipole moment that was going across this molecule that way. So anytime we have a polar structure, so the dipole-dipole is going to be associated with polar molecules that allow the negative side of one molecule to kind of bond to the positive side of another molecule. So they will kind of hitch up. One special circumstance of these polar molecules or dipole-dipole is what we call hydrogen bonding. And hydrogen bonding is a little bit stronger than just your standard polar or dipole-dipole. So hydrogen bonding occurs anytime we have hydrogen, nitrogen, oxygen, and fluorine. If those elements are involved in bonding, then we can get hydrogen bonding between those. So this particular one is polar and not necessarily just dipole-dipole. This would be hydrogen bonding between the H, the N, and the O, which is a little stronger than just your standard dipole-dipole moments there. So this is going to be hydrogen bonding in this case. Sometimes we can get a dipole-induced dipole, meaning a polar molecule can, kind of like a magnet, like a paper clip, get close to another nonpolar molecule and cause them to be temporarily essentially like magnetized, kind of like a magnet in a paperclip, where one side of it will be temporarily the opposite charge, the electrons pulling them away. That happens when you have very polar molecules attaching to very nonpolar molecules. And then if they are nonpolar, then we get this thing called London dispersion forces that will occur that will hold that particular group together. So let's look and see what ones we have for our. So for the one that we were just talking about, we know this would experience hydrogen bonding. We have an H, an N, and an O. So we're going to get hydrogen bonding. It's going to be our strongest intermolecular force. It actually has all of them. It would have London dispersion forces. It would have polar bonding. It would have hydrogen bonding. But when we talk about the intermolecular force, we're only talking about the strongest one that's going to occur, because this affects its boiling point. The stronger the bond, the higher the boiling point. Therefore, the more energy it takes to break the bond. The lower, so the weaker the intermolecular force, the lower the boiling point. Therefore, the easier it is to break the bond apart. With chlorine 7A, groups 7 electrons. There's 5 of them. So therefore, this is 35 plus 5. What do I have? I have 40 electrons available in this structure. We know phosphorus, once again, wants to get its 8. Chlorine wants to get its 8 times the 5 different ones. We want to get over, so there's 40, 48. Somehow I want to get 8 extra electrons that are shared. Therefore, it's saying that I want 4 bonds, but I know there's got to be at least 5. So maybe there's something weird that happens with phosphorus. And remember, why something weird can possibly happen is that phosphorus is in the 3rd row and therefore can potentially get a d orbital to be able to use extra electrons. So let's draw out what PCl5. So if I take phosphorus, and it's essentially 5 valence electrons, right? And now we're just going to get a chlorine that's going to attach to all of these. So we're going to get a chlorine attached to every single one of those. Okay, so 3-dimensional, what it kind of looks like, it's going to look like this, where 3 of them are all in the same plane. And then we have one of them that we call like going back. So we draw it kind of like this, going back into the plane. So I can picture that like going into the board. So usually we'll do it like that. And then, so that one's like going into the board or in, so that's right. And then one of them that's like sticking straight out at you. So we'll do the one sticking straight out at us like this. And there's the chlorine there. So we have 5 areas of electron density and gives us a different shape. So notice 5 areas of electron density tells me that this shape is going to be trigonal, right? And see, we did violate the fact that we were thinking that maybe it had 4 bonds, but so it does violate that because of that available d orbital that phosphorus has, right? So because phosphorus has that available d orbital, instead of forming 4 bonds, it can actually form the 5th bond using this available d orbital that phosphorus does have available. Not a super stable compound. It's typically, takes a little bit to make it, but it is still possible to make it. So the bond angles, these 3 that are red, that are all in the same plane, have a similar to the trigonal planar. So those 3 that are in red will be 120 degrees apart. And the 2 that are in blue there will be 90 degrees apart. So that's how those work, one being going into the plane, one going out of the plane. So that's how those structure. That's why we get 2 different angles. So there's some that are in the same plane and some that are in, one coming like out of the board, one going into the board, giving us these different weird angles. Now, as far as the polarity of each of these bonds, we do know that chlorine is a little bit more electronegative than the phosphorus. So let's look at those values. So notice here is phosphorus at 2.1, chlorine at 3.0. So yes, chlorine is a little more electronegative than phosphorus, so it would pull towards the chlorine. But what happens in the structure that causes this? So looking at the structure, yes, we do have electronegative. It's pulling towards the chlorine. It's pulling towards the chlorine. So those all cancel each other out. So all of these dipole moments will cancel each other out because of the 3-dimensional shape that this takes, making this be a nonpolar molecule. And because it has 5 things, we know the first one has to use an s orbital. There we can only have 3 different p orbitals, each 2, so that takes up 4. But where does the 5th bond come from? We said that was a d orbital. So for the hybridization, it would be sp3d. That is the hybridization, or the orbitals that are used in our bonding. And then looking at the last piece is that because it is a nonpolar structure, right? Because it's nonpolar, the only intermolecular forces holding this together is going to be London dispersion forces, and that is the only intermolecular force. And that's how we do all of these different components. Hopefully this was helpful and gave a little bit more clarity. Ask questions in class if you need help.